Hello guys, what's up? My name is Subham Kumar Agrawal and I welcome you all to my YouTube channel, that is the DU Chemistry. So today we have a very wonderful topic as so far we have done the statistical thermodynamics based upon those concepts. So what we are going to do, we are going to solve a very interesting question that is displaying to all of you in the screen. So let's first study the question, what the question is all about. Okay, so what the question is saying? The question is saying that consider the system of the three identical indistinguishable non-interacting particles. First of all, highlight the point distinguishable. Alright, so let's highlight it. So distinguishable. Alright, so distinguishable is the first point, and three non-degenerate labels are given us. Okay, 0E, 2E, and alright, so and the temperature T. Temperature we had studied so far that we used to keep the temperature of the system constant, that is T, and place the system in an isolated manner that no exchange of the energy would take place. Alright, so total energy is given 2E. Alright, and three particles, number of particles is 3. Alright, 3 particles are there, and what is asking? It is asking that the number of ways the particle can be distributed is. Alright, the number of ways the particle can be distributed is. So the number of ways means number of microstates. So ultimately what we have to find out? We have to find out the number of microstates. So I had already told you that in order to find such kind of in order to solve such kind of questions, first we try to make our macrostates, possible macrostates, then we find out the microstates of the corresponding macrostates, and then we sum up all those microstates, and finally we get our desired answer. Alright, so the same we are going to do right now. Alright, so as shown in the screen that I had already solved this one, that 3 energy levels are there. Alright, and the energy what is given to us that 0, E and 2E. So we had made the 3 energy levels and kept the energy of the system constant 2E. We arranged the particles in such a manner, in such a basis that the total energy of the system should be 2E. So we had kept the 2 particles in the 0 energy level and the third particle in the 2E energy level, so that when we calculate the total energy would be the 2E. The total energy of this macrostate A is 2E. Alright, now we are making the another macrostate, that is the macrostate B. Here we are doing the thing like we are placing the one particle in the 0 energy level and placing the other remaining 2 particles in the E energy level, so that we would get that the energy of 0 plus E plus E. 2 particles having the energy EE, so total energy would be 2E. Alright, so we had maintained the energy, the 2E, no other further possibilities of the macrostates. Alright, no further possibilities of the macrostates, so we have to be limited in this. Now let find out the microstates of the corresponding macrostates. So for first macrostate A, let's try to find out the microstates. So in the above in the upper side, what it is shown? It is shown that WA means microstates of corresponding macrostate A. So I had already told you the formula. And what was the formula? The formula was weight of oil. Okay, yeah. So number of particles, total number of particles, and factorial upon number of particles in each energy states of a macrostate A. So 2 are in 0 energy state, so 2 factorial multiplied by 0 factorial in the second energy state, and one particle in the third energy state. So on calculating we get the answer 3. Similarly for system or say macrostate B, the total number of particles is 3 and the 0 factorial one particle in the 0 energy state, so 1 factorial into the 2 particles in the first energy state, means E energy state, so 2 factorial, and we get the answer 3. So 3 microstates in macrostate A as well as 3 microstate in the macrostate B. So summing on after summation of all both of them, we got answer 6, means 6 microstates, total 6 microstate possible for this system. Alright, so here we had also made a generalized expression for it, and like what is written here, ways of arrangement of a macrostates, ways of arrangement of a macrostate. So finally from those macrostates we find out the microstates in each macrostate, and what is given here, it is given the formula for a generalized manner that for any of the system you can find out by using this formula. So this is not a very tough, very easy formula. N factorial means total number of particles, and factorial or pi I means the multiplication, similar to the sigma refers to the summation and pi refers to this multiplication. So Ni means number of particles in each energy state of a particular one macrostate. Alright, so we find out the microstates for a particular one macrostates. Alright, and then finally we add all those microstates to get the number of microstates for a numerous macrostates. Now we are introducing the new concept, that is the concept of degeneracy. The concept of degeneracy, first try to understand what the degeneracy is all about. Degeneracy refers to the energy states having the same energy. Number of energy states having the same energy, we call those energy states as degenerate states. Alright, are you getting what I am saying? That number of states having the same energy are termed as degenerate states. Alright, so what here is given, I had here written the degeneracy of some of the energy states already, as well as I had written the number of particles N0, N1, N2, N3 along with their energies. So what we are going to do, we are going to take one particular energy level. We are going to take one particular energy level and then discuss, like we are taking the ground energy level, like N0 number of particles with E0 energy and having G0 degeneracy. Alright, so let's start. So for E0 energy there are G0, there may be the G0 degeneracy, means G0 can be any number and those particular number of states are in the same energy, and I had represented in like manner like this, and G0 can be any number. Alright, so now for a particle, if you want to arrange them in a manner such like that, you have to put in the G0 states. So for each particle there are G0 states. For each particle there are G0 ways of arrangement of that particular particles, है ना? There are G0 ways of arrangement to put or to arrange that particle in the energy state in E0, and for each particle, for one particle G0, for two particle, for second particle, for third particle, for fourth particle, as well as for N0 particle, there are G0 ways of arrangements. Alright, there are G0 ways of arrangement. And one more thing, that there is no restriction. So that there is no restriction, like we cannot arrange the particles in the same, we cannot put more than one particles in the same energy states. There is no such restriction we have. We can arrange as many particles in any of the energy state. Alright, what I mean to say in a particular one energy level you can put more than one particle. 2, 3, 4 or even n naught particles. So for each particle there are g naught ways of arrangement possible. Alright, so for a generalized way, in a E naught energy state, total ways of arrangement is z naught in times n naught. First z naught is for one particle, the second particle it is z naught, for third particle it is also z naught, and for n naught particle, up to for n naught particles there are z naught chances to arrange it. Alright, so on summing up, we get W equals to g naught ki power n naught, g naught raised to the power n naught, and this extra factor is coming due to the degeneracy. G naught factor, why it is coming? Otherwise we have n naught only particles. Otherwise we have only n naught particles in the first energy state. But when we introduce the concept of the degeneracy, we got to know that there are several more ways of arrangement of those particles. There are more ways also possible for arranging those particles, and when we had studied all those arrangement, we got to know that this extra factor is coming, and ultimate formula is W equals to z naught raised to the power n naught. Alright, so hope you might be clear with this concept. Now we had taken this for a one energy level, that is the E naught energy level, and if we have to sum up for all the system that we had taken, I mean for G naught energy degeneracy, G1, G2, G3, are you getting my point? That for a whole system, if we arrange this formula, then we have like yes, then we have ways of arrangement after including the contribution of the degeneracy. When we had included the contribution of the degeneracy, because degeneracy is somehow to a little extent it is contributing. Alright, so the number of ways of arrangement the formula has given below, and have a look at least. So W equals to n factorial, what we had studied so far, n factor upon, n factor means total number of particles, upon pi and ni factorial. Alright, but on introducing the concept of degeneracy, we got to know, on expanding the pi, we got n naught factorial, n1 factorial, n2 factorial, and so on, and with them there has the degeneracy as well, and degeneracy are like z naught to the power n naught and z1 raised to the power n naught, and so on. Alright, now what we had made a generalized formula for this as well, and we had put all the terms in a short manner and given to you that ni we had taken it outside, and inside of the formula we have pi I and zi to the raised to the power ni upon ni factorial. Alright, so this is the generalized formula. Alright, okay. Take a breathe, calm down. Take a breath, calm down. Okay, let me also take the breath because I got alright. So now what was our aim? Why we are studying these microstates and arranging and applying the approximation, assuming so many of things? Our primary goal, our primitive goal was to find out the actual macroscopic property of a system. What would be the macroscopic property? That macroscopic property might be anything like entropy, enthalpy. But here what we are working over a system having the our goal is to find out the macroscopic property. Alright, so for that macroscopic property we have to find out the maximum probable microstates. Maximum probable microstates refers or meaning is that the particles or the microstates where those microstates spends most of its time. where those microstates it spends most of its time, like we can say that we can also say that most probable macrostates. And according to this second postulate, what it says that the property average equals to time average. And what it means that where the particle spends most of its time, that position is known as most probable. And the property where we determine the average property that refers to that particular most probable microstates referred to as most probable property. And that particular most probable microstate refers to a property according to the second postulate. According to the second postulate, property average equals to time average. Alright, so we got to know that by summing up what I want to say that alright, I want to say that where the particle spends most of its average time, that would be the most probable that would be the most probable microstates. So that probable microstates, when taking in a formula, then S equals to K ln W max. W max equals to most probable microstates, and according to the second postulate, property average, that is the entropy. Entropy is the property, and equals to the time average. Time average W max. Why W max? W max is the where the particle spends most of its time. Where the particle spends its most of its time. So we have generalized this formula, and very important formula, try to mug it up right now. S equals to K ln W max. Alright, now we are going to do one question which is shown up to you. What it is saying, let's read the question. The number of configuration. The number of configuration means number of microstates, and number of microstates, which type of microstates? In the question, what it is saying, in the most probable macrostate. In the most probable macrostates means W max. It is talking about the W max, means most probable microstates. Alright, according to the Boltzmann formula. So this formula also known as the Boltzmann formula. Boltzmann formula. Try to write it down in your notes. And what it is saying that the number of configuration means we have to find out the number of microstates. So on taking this formula, and we had solved that W max equals to E की power S upon KB. E की power S upon KB, this is the number of configuration in most probable state. Alright, so what the options are given? E की power S upon KB, E की power minus S upon KB. So what is the right option? A1 is the right option. Option A is the right one. Alright, now moving onwards. Okay, so this is the very generalized equation that has given to you, but this has came from a very big expression which comprises of 4-page expression. So I had not explained that one with you because it has a lot of assumptions and big mathematics. There we had used Lagrange as well as Stirling's operation and approximation. So there we had a lot of we have to put our mind, but the actual summary or conclusion what came out is what is written to you, that this formula is very important formula. You have to write it down and mug up, because it gives you the configuration of most probable macrostate. Alright, so basically if you try to understand, then I can explain you like for example, there are 4 energy states, and you know that the total number of particles are like some like 4 or 10. There are total number of particles, but if you have to find out the number of particles in any of the state, I mean for the first energy state or the second or the third or the fourth one, if you have to find out the number of particles in any of the energy state, then you can find it very easy manner by using this formula. Alright, because you were knowing the GI means degeneracy of that particular energy level, and the beta is equals to 1 upon kBT. I have written in the next slide, but try to note it down. Kb equals to Boltzmann constant, and T refers to the temperature. So you are knowing very all these things. So you can calculate any of the number of particles in any of the state. Alright, so this is the system given, and what we call the macrostate or the most probable macrostate, all these particles where the most probable macrostate is there. Alright, now moving to the next slide, what is given to here. There I had introduced the one concept of configuration. So what we call the configuration, I had said that are the microstates. So microstates are basically the number of particles in each energy states. Alright, so n0, n1, n2, n3, these are basically referring the configuration. Alright, these are basically referring the configuration. And ni upon n, which I had told you in the earlier formula, it is basically the probability. It is basically the probability of finding the particle in ith state. The probability of the finding of the particle in the ith state. Why we are considering the probability? Because we cannot find out in a very because we had made approximations. We had applied and assumed, by assuming a lot of approximations, we had concluded to that formula. So we cannot say very firmly, we just put the probability. Alright, so probability is pi, and this is the formula. So this was the formula. Alright, and this beta equals to 1 upon kBt. This beta equals to 1 upon kBt. This was the formula. Alright, now we are going to introduce one thing, that is the partition function. Yes, might be you had heard about it, and this is the thing that you will going to study in a whole throughout the statistical thermodynamics. Alright, so what is this? This is the partition function. This is the partition function, and what the partition function we will study later. Alright, but here why I am introducing, because in the formula the lower side, the denominator side, what the expression is written, this actually refers the partition function, and this is the single particle partition function represented by small q. This is the single particle partition function represented by small q. So this is basically the partition function, and which came from this formula, and we will study a lot in this particular subject. And here we are written this, and this partition function is the function of only of temperature. If you change the temperature, then this partition function changes, otherwise no change in the partition function occur. So just mug it up, and we had just concluded the formula. We had put here q and nothing different. Alright, so hope all the things which I had presented here, you will be very clear of that. If you have any doubt, please write in the comment box. I will definitely answer it, and yes, we will meet in the next video. So till that, see you, have a good day, bye bye.